All right, here we go, Tate. This is chapter 1. We're going to try to get through, I don't know. We have 4 chapters, right? Maybe we can get through all chapter 1. 15 questions. Let's do it. I bet we can. There's 40 questions, so we need to get through at least 13, but chapter 1 would be 15. Let's try to get that far. Okay. All right, we start with limits. Okay. Rule number 1 for limits. Like, what is a limit, by the way? Yeah, it's like what the y coordinate should be, right? Okay, so as x approaches something, it's like what the y coordinate should be. Now, a lot of times, there will be a vertical asymptote there, or there'll be a hole there, right? And it's like, okay, if that hole wasn't there, what would that value be, right? That's what a limit is, okay? First rule to limits. Always attempt this. Always try to what? Like on number 1, what's our approach? Always try to plug it in. Try to plug in. Rule number 1. Always try to plug the dang limit in, right? So this is your flow chart. I'm putting a flow chart off to the side of like, here are strategies of what to do when you don't know what to do with a limit, right? So number 1, can I plug in? Probably. So if I plug 1 in, or if I plug 2 in, right? 2 squared is 4. 4 times 2 is 8. 8 plus 1 is 9. So we're looking at the square root of 9, which is 3. Is it plus minus 3 or just 3?
Just 3.
We did not insert the square root in there. Like, we're not solving for anything. So it is just like imagine that there's a plus sign out in front of that, yeah? So it is just 3. So if, I guess here, there is no hole or there's no va, right? So there is an actual physical y coordinate, right? Now, I, beg the question, why do we even try to find a limit if there's not any funky business like a va or a hole happening? Like, that was dumb. The y coordinate is the same as the limit, but whatever. Okay, number 2. Can we just plug the dang thing in? No, because why? Right, 0 on the bottom. So we have to decide, what does that do? Like, what is there? No, it's not a hole. Hole is where it cancels to the top and bottom. So there is a va here, okay? So, number 2. This is if it fails, right? Okay? So, if fails. Number 2, it could be a va, right? So you have to know whether it's a va or a hole. If it is a va, look at the graph. So we'll talk about what the graph looks like here in a second, okay? So if it's a va, we're going to look at the graph, all right? I know that there's a va at 2. So I have this thing going on, and here's a va at 2, 1, 2, blah, 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 right? I know there's a va, okay? So I don't know, actually I do know, something is happening. Like either it's going like this, or it's going like this, or it's going like this, or it's going like this, right? Okay? Now, what we did before was we just plugged in numbers that were really close to 2, right? Okay? So let's plug in really close to 2, like 2.01, right? If I plug in 2.01, right, that would be like on this side. I need to figure out whether he's going to infinity or going to negative infinity, okay? So 2.01 minus 2 would be 0.01, and if I square that, that's 0.0001, right? 1 divided by a really, really, really small number is going to be a positive number, right? It's going to be positive. We don't even really care what it is. It's going toward infinity. So it's doing that little loop right there, right? Okay? If I plug in a number that is blah, blah, blah. If I plug in a number that's really, really, really close to negative 2, or to 2 on the other side, like let's say 1.99, that is negative 0.01, but by the time I square it, it's again 0.0001. 1 divided by that is positive. So it's doing this. Do you know that 1 over x squared, his parent function, looks like a volcano? Do you know that? Yeah? Maybe we need to add that to the list over here. So, 1 over x squared looks like this. Just for your information, 1 over x looks like this. If you feel the need to add those, you sure can. Oh, that's a really bad graph on that side. Let's do that again. And now it's really fat. Whatever. I'm struggling. Okay, here we go. So, maybe if you need those, whatever, okay? So, what is this limit? The limit equals infinity. It's approaching infinity on the other side. Okay, what happens if it's approaching infinity on one side and negative infinity on the other side? Does not exist, right? So, does that make sense that if I say if it's a vol, look for the graph, right? Like look at either side. Plug in close numbers. Okay, there you go. All right. Let's skip down to 4 real quick. Okay, can I plug in negative 9? No. Is there a VA at negative 9? Potentially. It looks like there is, right? Because if I set this guy equal to 0, it looks like there's a VA, right? Okay. But it could be a hole instead, right? Depending on what this thing looks like, right? So what do? Factor it down, right? Okay. So this is a simple trinomial. What do you multiply to get negative 27? When you add them, give you 6, right? And they are x plus 9 and x minus 3, right? Okay, negative 9 is in fact a whole, right? Okay. So now I'm just looking at the limit as x goes to negative 9 of x minus 3. And now, can I plug in negative 9? Sure I can. And if I do, I get negative 12. So there is a hole at the coordinate negative 9 comma negative 12. But if that hole didn't exist, there would be a solid dot filled in on 12, on negative 12, right? Okay. So strategy number 3 is if it's a hole, you're going to factor, and I'm going to say delete the hole, and then plug in. Does that make sense? If you need to make that make more sense, write it in some different terms, but whatever. Okay, good? Okay, now, sometimes, number 4, you have equations that look like this, and these scream like one strategy to me. Whenever there's a square root, I'm like, oop, I know it's got to be this, right? First of all, can I plug 0 in? No. It looks like there's a VA at 0, but then I have the square rooty thing going on at the top, and that's really disgusting, so I'm going to do something different. What would you like to do? There is like one strategy they have to use on problems like this, whenever you have a square root. You remember? What? Yeah, rationalize if there's a square root. That is your strategy. That is your strategy. Okay, how do I rationalize? What are you going to multiply by? The reciprocal. What's a reciprocal? What's a reciprocal?
X plus 1 minus 3. So this negative, right?
It's negative in front of what? What'd you say?
Isn't just a negative over under the positive? No.
You don't change the sign. He stays the square root of x plus 1. Normally, when you rationalize, you change the signage of the square root. Like you change this guy's signage, right? So this would become negative minus the square root of 3, or minus the square root of 3, minus 3, right? Okay? But for this, no, you wouldn't change the signage of this, right? Of 3. You only change the signage of the square root, okay? But for this process, you can actually just change the signage of the middle term, right? And it doesn't screw it up. I don't know. Maybe it will screw it up. Let's just find out. Plus 3. Okay, we're going to do that. So we can change the sign of that middle piece, but what we do to one side, we have to do to the other side. I'm going to deal with the bottom first. Do not. Do you remember my warning? Do not multiply the x through. Leave him to look like this. And do you remember why? Because he's going to cancel out at some point, right, from the top. All right, so what do we do at the top? We gotta FOIL them. Okay, what's the square root of x plus 1 times the square root of x plus 1?
2 squared root of x plus 1.
It would be like the square root of x plus 1 squared.
X plus 1.
It's just x plus 1. It just falls out, right? Like the square root of 3 times the square root of 3 is just 3, right? If you take the square root times itself, it will go away, okay? All right, if I take this guy times 3, that is plus 3 square roots of x plus 1. But then I have my middle two pieces minus 3 square roots of x plus 1. So those middle two pieces just go away. And then I have minus 9. There's a typo in here. Yeah, this is a typo. This has to be 9 right here. Can you change that? 9. So this guy comes out to be 9. Yep. Otherwise it doesn't work. I remember this being a thing. That 1 is supposed to be a 9. So all the 9s need, or all the x plus 1s need to be x plus 9s. Can we do that? Is that manageable? So, on the top, we are left with x, because the 9s go away. On the bottom, x times all the junk, right? The square root of x plus 9 plus 3 and all the things. Cancel, cancel. So what's left on top? 1. All right, now, are you able to plug in 0? Yeah, so I get 1 over the square root of 9, which is 3 plus 3, which is 1/6. Does that work? Kind of an awful process, right? Yuck, yuck. Okay, rationalize, rationalize. Okay, 5. Are we ready for 5? Are we happy with that? Happy with 4 and 3? 5, let f of x be this guy, which is a rational function. He has a va at 1. This guy's an x to the 4th power function. He is a w. Find all the values for which f composed of g of x. This is like f circle g x, right? This is fog. So what's that mean? You put one equation into the other. Which one goes inside? G goes into f, right? Okay. So f was originally 5 over x minus 1. But now that is x to the 4th power. Okay, find the values where this thing right here, and those parentheses aren't doing anything, so I just have 5 over x to the 4th minus 1. Great, okay. Find the values for where this thing is discontinuous. Okay, what makes something discontinuous? A hole? Or a va? Or what else? A jump, which occurs in piecewise functions that don't match up, okay? We don't have a piecewise function. So we either have a hole or a va. Which one? Probably. Holes cancel with the top. I'm not going to have anything cancel with 5, right? Okay? So I'm looking for vas. How do we find a va? Bottom equal to 0. Okay, so if I do that, x to the 4th minus 1 equals 0. X to the 4th equals 1 if I add the 1 over, right? And then I take the 4th root of 1. Okay, 4th root means what do you take times itself 4 times to give you that number, right? What do you take times itself 4 times to give me 1? And? Negative 1, right? Negative 1 times itself 4 times. Okay, so I actually have 2 vas, okay? And the fact that I have 2 vas means that he's discontinuous at 2 places, right? Discontinuous here. At 1 and negative 1. He has bad things. Bad things happen. Okay, number 6. This is a what kind of function? Okay. If piecewise, we didn't really have a rule because we weren't actually evaluating a limit for number 5. But if it's a piecewise, plug in to appropriate equation. And you're like, what the heck does that even mean? Plug it into the appropriate equation. Okay. I'm going to extend number 6, problem 6, and we're going to do a little bit more work than we need to, but I want you to be prepared in case I ask something different on the test. So, they are having you find the limit as x approaches 1 minus, okay? All right. We are also going to find the limit as x approaches 1 plus, and we're going to find the limit as x approaches just 1, right? Okay, and we're going to figure out what those are. All right. When I say plug it into the appropriate equation, if we're doing 1 minus, this means approaching 1 from the left. Which equation approaches 1 from the left? The top one, right? The top equation, that's less than 1, right? So I'm going to plug 1 in here, and I have 1 squared plus 4, and that is 5. So, approaching 1 from the left, it's going to approach a y-coordinate of 5. Now, it actually doesn't even have a hole at that point, right? There is actually a physical number at 5. How do I know that? Because it's equal to, right? Greater than or equal, or less than or equal to, right? Okay. Now, we are going to have a hole when it's talking about 1 plus, because 1 plus is not equal to, right? So if we were to graph that thing, we would have an open circle or whatever, okay? If I plug 1 in there, 2 times 1 plus 2 equals 4, right? So 1 plus is going to be 4, right? Okay. What about the limit of as x approaches just 1? 1 from the left is 5, 1 from the right is 4. So just 1, if we're looking at both sides together, basically.
Isn't it equal to 1, so we can plug it into the top one?
Nope. Like if I graph this thing, right? Like this, you don't write this down. Don't write this down. This guy,
Not exist.
They're not the same, so it does not exist, right? They're in disagreement with each other. Even though it's equal to at 4, right, or at 5, I guess, equal to at 5, it does not exist because it's what the y-coordinate should be. Well, the left side's telling me it should be one thing, and the right side's telling me what should be the other thing, right? So it does not exist. So what we have, what we have going on here, this guy, this first guy, is up at 4, and he looks like this, right? And he has a closed circle, right? So he's touching at 5. This is where 5 is, okay? And the other one is touching at 4, right? And he's an open circle, and he's going like this. He's a linear function. So whatever, right? And the fact that there's a gap there, right here, this gap, this is at 4, by the way, this tells me that they're in disagreement with each other. Now, do you ever have it where the limit does exist? Here? Yeah, that would take place if, let's say, I had like this function going like this, and it's an open circle and a closed circle like that, right? Like if they're touching each other, right, where it's completely continuous all the way through, yeah, we still have two pieces, right? But if they're touching each other and they're overlapped, that's where I will actually have a limit for both sides together, right? Okay, and that has to be where like these two are the same number, right? So, I just want to prepare you. Yes, it was only asking for 1 minus, but if I ask you both sides together, do the left and the right and see if they're in agreement. If they are, great, it's that number. But if not, limit does not exist. Good? Okay. Find the values for which this thing is discontinuous. Okay, let's just do that first. Discontinuities are vase, holes, and piecewise functions, right? But this is not a piecewise, so we don't have to worry about that. But we may have some vase or holes, right? How do I find them? How do you find vase and holes? Bottom equal to 0, right? If I set the bottom equal to 0, okay. Do you want to treat this like it is a difference of squares? Yeah, we'll just break them down. Okay, let's do that. Or you can add the 4 and take the square root, right? Whatever, okay. So X plus 2x minus 2. Okay, what? And so I'm going to have something happen at negative 2, and I'm going to have something happen at positive 2. And they both look like vase right now, except which one is actually a whole? X equals positive 2, because x minus 2 cancels, right? So this guy is a whole, and this guy is actually a va, okay? But it's discontinuous at both places. So discontinuous here. At 2 and at negative 2, he's going to be discontinuous. All right. Now, here's the tricky part. It says, which of these discontinuities is removable? What the heck does that even mean? What? No. Which one removes? Which one removes? Right? Basically, a removable discontinuity is asking for where the whole is. A removable discontinuity where it cancels out. A removable discontinuity is at the whole, and the whole is at x equals 2. That's the removable one, right? Make sense? Man, it's been a hot second since we've done limits, right? Is it all coming back to you? You having nightmares yet? Okay. All right, 8. They'll start to hopefully go a little faster now. Okay, find the limits. X goes to negative 4 minus. Can I plug negative 4 in? No. All right, you have all the rules. Which rule does this one fall into? Those are all the rules. Plug it in, fails. What? Look at graph. What does this graph look like? I know he has a what? Why does he fail at negative 4? He has a va at negative 4, right? Okay. And we are particularly looking at negative 4 from the left side. So we want to plug in numbers on the left side of negative 4. Okay. What numbers are left of negative 4? I was waiting for somebody to say negative 3.99, right? Because they're like, left means less than. 3.99 is technically over here. Okay. Didn't fool ya. All right. So I'm going to plug in negative 4.01, right? 3 over negative 4.01 plus 4, right? Okay. 3 divided by, if I add those two together, that's negative 0.01, all right? Doesn't really matter what that is. I know it's going to be negative. So he's approaching that. That's what he looks like, right? And so he's approaching negative infinity as he gets closer to negative 4 from the left. So limit, negative infinity. Good? Happy with that? All right. Beautiful. Oh, man. Look, number 9. This is exactly what I warned you about. Shoot, I should have just waited till we got here. The limit as x goes to 3. From which side? Both sides, right? So let's do x goes to 3 minus, x goes to 3 plus, and let's just compare. X goes to 3. Okay. All right, 3 minus is 9, right? If I plug 3 minus into here, this is 3 minus. So 3 squared, which is 9, okay? 3 plus is 2 times 3. 2 times 3 plus 4, which is 10, right? So just 3 does not exist. This is my final answer, right? Because they are not in agreement with each other. So 3 in total does not exist. Good? Happy with that? All right. Now, everything that we were talking about before is all null and void right now. Because now, starting with 10 and 11, now we are doing infinite limits, right? We're plugging in infinite limits, okay? So the rules only apply to limits as x is approaching a number, right? As x approaches a number. These are not infinite limits. We have different strategies for finding infinite limits. Infinite limits are looking at what's happening forever on the right side and forever on the left side. So infinite limits. This means like left side slash right side, like what's happening on the very left and on the very right. And usually what's happening is he's like approaching a horizontal asymptote, right? Like on the left or the right side. Maybe he's not approaching anything, I don't know. But usually he's approaching a horizontal asymptote. So this has a lot to do with finding the Ha's. Finding Ha's. Yeah. Okay. How do you find a Ha, by the way? We know this. 1, 2, 3. N equals M equals, right? N is the degree of the numerator. M is the degree of the denominator. Okay? If N is less than M, that means he is bottom heavy. So the limit is going to be 0. Right? Like y equals 0 would be the Ha. So the limit is 0. Okay? If N is greater than M, that means he's top heavy. He's going to fall over. The limit does not exist. Does not exist. Because there will be no Ha, right? He's not going to approach something. Okay? And 3, N equals M. The limit is LC over LC. Kind of like y equals LC over LC. Okay? Okay? Those are your rules. So number 10. Am I going too fast? Okay, number 10. We're going up to infinity. So this is like saying what's happening as he goes forever to the right side. Is he approaching a Ha? Does he have a Ha? Yeah. The Ha is going to be at 2/3. So the limit is going to be 2/3. Okay, now what we don't know is, we could probably take a guess. So the limit's at 2/3, so that's what's happening here, blah, 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 blah. We know that as he approaches to the right side, he's going to approach that. I don't know if it's from the bottom side or if it's from the top side, but I don't really care, right? Doesn't matter. The limit's going to be 2/3 no matter what, right? I don't care if it's from the bottom side or the top side. 2/3 is the limit. Good? Okay, what about 11? As he approaches negative infinity, does that matter? He's just saying as he approaches forever to the left, right? Doesn't really matter. Okay, we're still looking at Ha's. N is 1. M is 2. He is bottom heavy, so he's approaching 0. Right? I don't know if it's approaching 0 from the bottom side or the top side. Don't really care. It's going to be approaching 0 as it goes out. Okay? Limits. Oh, good old limits. How are we feeling about limits? Does it help having a flow chart, kind of, ish? Okay. Infinite limits you treat differently than limits at specific numbers. Okay. Now we're doing, actually, I don't know why. We switched to logs and we switched back to limits. Can we go to number 15 first, and then we'll go do some log stuff. This guy is saying as x goes to -4 from the left. Okay. What should the y-coordinate be as he's going to -4 from the left? What? So if it was approaching, if we're talking about approaching -4 in general, right? -4 is right here. So from the left and the right side, the fact that they don't match up means that -4 altogether does not exist. But -4 from the left does exist. It is at 6, right? Like the y-coordinate right here from the left side coming in is touching 6. So, yeah. Okay, good? So just be careful whether you're saying from the left, from the right, or both together. Okay? Good? Beautiful. All right, let's do some logs and then we'll stop. Right? 3 more? Can we handle that?
Yeah.
All right, to rewrite the expression as a single log, how many pieces do I have? 3. 1, 2, 3. All right, before we start putting stuff together, I know add means like plus means multiply and minus means divide in log world. But before we do that, before we start shoving stuff together, what shall we move? What? Yep, the numbers that are in front, bring them to the back, right? So this is squared. What about the 1/2? Yeah, when I bring him back, he'll be the square root of y. 3 will be z cubed. Okay, plus means, okay, so we have 1 log, right? That's all getting shoved together under 1 log, right? And I'm going to have like maybe some stuff here. Okay. Plus means multiply, minus means divide. What's this look like? X squared, square root of y, bottom of z cubed. Am I done? Yeah. Express it as a single log, it's all together. Was that confusing? Now they're wanting us to tear it apart. Does it matter that it's ln and not log? No. How many pieces are you going to have? 3 pieces. You see them? This guy, this guy, this guy. Okay. So I have ln of something. I have another ln of something. And I've got another ln of something. Okay. What? Yeah, so these two, since they're both on the top, it's going to be plus. The bottom's going to be a minus, right? Okay. All right. So if I pull them apart, like x squared goes here, x minus 1 goes here, and x minus 2 cubed goes here, right? Okay. Done? Almost? What? What else? Exponents in front. Yep, that's the last thing. So it's exactly the opposite steps as what you did before, right? So 2 ln x. I don't really need parentheses around my x, right? Because he's only one piece. Do you need parentheses around the x minus 1? Yes. Because otherwise, if you do x minus 1 like that, it's ln of x and then minus 1. So you want it to do the x minus 1 first, so that has to go in parentheses. Minus 3 ln x minus 2. Same thing, he needs parentheses, and that's it. Last one. Okay, we're solving for x right here, but x is in the exponent, so this requires us to do some things. First and foremost, divide by 3 first. We gotta get rid of the 3. Yep. So we've got e to the negative 5x equals 9. Now ln, because ln and e cancel, but they have to be right. Why did I put that so weird like that? Blech. Equals 9. 9 is down. All right. ln. Okay, so I have negative 5x equals ln 9. And then what? Divide by negative 5. So ln of 9, either hit enter or close your parentheses or whatever, divided by negative 5. X equals something. Perfect. Sure. Sounds good to me. Okay? Happy with that? We're remembering all this stuff again? All right. Tomorrow we will... Oh, man. We got derivatives tomorrow. Man, oh, man. Okay. Sounds good. All right. Bye, Tate.